So we call these many body problems, more than one mass. In these problems, Rick, we have several objects connected together by strings. And because they're connected together by strings, because they're going to accelerate at the same rate, here is our clever trick. Alec, we're going to treat them as one big Ubermass. Find the acceleration, and then go look at individual masses to find individual forces. Let me give you an example. Example 1 says this. Find the acceleration and the string tensions, and it says in brackets, use the system approach. We're going to treat this as one big system. We're going to start out with a free body diagram, although typically, Taylor, if I have multiple masses, rather than doing a complete new free body diagram, I just start to label the diagram that they gave me. Okay? We have no friction. We'll build friction in later on today. And I'm going to start out labeling my forces. I tend to label from the left to the right. You don't have to do it that way, but if you want all of your subscripts to match mine, do it that way. So, Devin, we're going to start with this 3 kilogram mass. What are the forces acting on it, my friend? Get the obvious one. Is there more than one mass in this question? So I'm going to call it M1G, and I'm going to call this mass 1. Is M1 sinking into the ground like quicksand? Is it flying into the air like Superman? So the forces are balanced. Net force is 0 in the vertical direction. So what else must there be, Devin? Is there more than one normal force in this? You know what? I'll call it normal force number 1 to go with mass number. There you go. What else, Devin, my friend? Stop. Not done yet. Is there a rope? So what force does a rope exert? What you're feeling right now. Tension. Is there friction in this question? If there was, I'd have one more force pointing that way, and it's really not that big an extension. Your question gets longer and uglier, but I can't say it gets more difficult. It's just more typing. Those are the 3 forces acting on mass 1. What are the forces acting on mass 2? Get the obvious one. More than one mass, I'm going to call it M2G. What else? Go systematically. We just did M2G, normal force number 2. What else? Which way? That way? No. Where's the rope? Between the two of them? Now that is because of forces come in. That's in Newton's third law. And I'm going to argue the tension in a rope will be the same throughout the rope. It's impossible to pull on a rope and have someone feel 10 newtons at one end and only 1 newton at the other. And ropes don't work that way. No, that would have to have slack or something in the rope for that to be the case. Okay? And then we have one more force that's labeled on there. It's that 20. This is coming from off the page. Some invisible angel or leprechaun is... What do we call that force often? This is the applied force. I'll put an arrow here and I'll write equals F applied so I don't miss it. So I tend to put tension right on the rope, not as a separate arrow, because I want to remind myself that they're part of the rope. Those, Pauline, are the forces acting on those objects. Do we have friction, Devin? So we're on ice. Perfect ice. Frictionless ice. Do I have an unbalanced force? Yeah. To the right, that 20. So which way must this whole thing accelerate? To the, loud and proud, I'm going to ask you the same question, I'm just going to phrase it differently. What direction is the winner going to be? Anything that ends up pointing to the right, Taylor, I'm going to put a winner plus sign in front of. Anything that ends up pointing to the left, I'm going to put a loser minus sign in front of. And I'm going to get the equation by walking along the entire rope. So, Devin, let's start on the far right side of the rope, walking along the rope. What's the first force you run into? So my equation is going to look like this. Winner. Keep walking along the rope, keep walking along the rope. What's the next force you run into? Tension. Loser or winner? Loser. Minus tension. Keep walking along the rope, keep walking along the rope. What's the next force you run into? Winner or loser? Keep walking along the rope, keep walking along the rope. Are there any other forces along the rope? No, there's no other forces in my equation. This bugs people. Kids are, whoa, what, M1G? No, they're not in the same direction as the rope. Don't you dare. Don't put a horizontal into a vertical or a vertical into a horizontal. Equals. Now, normally, winner minus loser equals MA. Who remembers what was the slight adjustment we had to do if we had forces from more than one mass, which we do have in our left-hand side? What does the right-hand side look like? The short version was M all of them times A. M all times A. Devin, why am I so relaxed? I'm losing tension? Oh, I like that. I love it when I lose tension. It's so relaxing. Some people pay money for that. You can do it just by doing some physics. People go on fancy spa vacations. No! Do a little physics. What was the first thing it wanted me to find in example 1, Dev? How to get the A by itself. And I love the fact that this complicated situation, we actually end up with a pretty clean equation. We have the applied force divided by both masses. Devin, what was the applied force as a number? What was mass 1? Mass 2? Holy smokes, Devin, I bet you can do that in your head. 4, like when I play golf, what I say a lot, 4. I'm a horrible golfer. And I'll go to 2 sig figs, so I'll go 4.0. It's an acceleration. Units? Okay. So our strategy, if you give me multiple masses, I'm going to write a big uber equation for everything. It's going to equal the mass of all of them times A, and then I can find A. If I do it right, tension will cancel. Then, if I want to find... He already has, thanks. If I want to find individual forces, I go look at an individual mass. Let's look at mass 1 to find tension. Devin, look at mass 1, look at mass 1, look at mass 1. Oh, heck, let's redo the free body diagram. What were the forces acting on mass 1? We had M1G, normal force 1, and tension. Which way is mass 1 accelerating, Devin? Who's winning? Look at my diagram. Which way is mass 1 accelerating? Who has to be winning? Has to be tension. Okay? No hesitation, guys. No hesitation. Got to be tension. Who's losing? Thank you. No one. Every time I see kids, graph it? What? No one. So winner minus loser. What does winner minus loser always equal? Which mass this time? M1A. Because we wrote this equation from mass 1. There, tension. What was mass 1? What was A? Holy smokes, Devin, I bet you can do that one in your head as well. What's the tension? Oh, I like that. And newtons. Wait a minute, Mr. Dewick. You might be saying, Daniel, wait a minute. What if we used mass 2? That's a great question, Daniel. That's a great question. So in mass 2, we had M2G, normal force 2, the applied force, and tension. Daniel, my friend, what direction is mass 2 accelerating? To the? So who's winning? You can't read that worth a darn. Let me try that again. That's slightly neater. Who's losing? Okay, and I'm going to stop. I'm just writing an equation for that mass. So my equation would end up being F applied minus tension equals M all A? No, I'm only writing one mass. Which mass? M2A. Daniel, what's right in front of the tension that I don't like? What's right in front of the tension that I don't like? No, right in front of the tension that I don't like. You're way overcomplicating it. Yeah. We do the swappy dance. Remember that from last year, folks? We're going to go plus that over, minus that over, and we're going to end up with this. F applied minus M2A. That equals tension. Daniel, how big was F applied as a number exactly? Minus, what was mass 2? 2. What was A? We calculated it somewhere, I think. Or if you're writing this down, I hope you are. In your head, what's 20 take away 8? You know, it'd be really cool if it was the same 12 that Devin gave us. Is it the same 12 that Devin gave us? So the nice thing about this, Bryce, is it doesn't matter which mass you use, although one will usually be cleaner. I tend to use the one that's easier or cleaner. Okay. That's going to be our strategy. You give me more than one mass, I just treat it like one mass to get the acceleration. And then I can find individual forces by writing individual equations. What if we have several masses connected by strings? If you have more than one string, this is going to sound Captain Obvious, but you have more than one tension. That's it. That's how it's going to work. Pierce, example 2 says find the acceleration and chord tensions. We're going to try and do this with as little writing as possible. You're not going to be able to get away from labeling your forces with a free body diagram. So let's start. Is there friction in this question? So we're going to ignore that. If there was, I just have some extra forces. Meh, I could deal with it. What are the forces acting on this 3, Pierce, my friend? Get the obvious one. Is there more than one mass? I'll call it M1G. What else? Is there more? You know what? I'll call it normal force number 1 to go with mass number. What else? Is there more than one rope? Then I'm going to call this tension 1. What else? Is there friction? If there was, I'd just have one more force pointing that way. It's really not that much more difficult. Longer. What are the forces acting on mass 2? Get the obvious one. I totally agree. I'll call that M2G. By the way, don't start just writing mg, because later on you'll cancel out m's that aren't supposed to cancel out. Label m1, label m2, label m3 always. What else? Normal force number what? To go with mass number. What else? Which one? Which way? So which way pointing to the left? What will I call that? To the left? Because it's the same rope as tension 1 on the other side. That's going to be tension 1 as well. Same rope, same tension. On the right, new rope, tension 2. Now, if you look at this, here's also what we're saying, by the way. Tension 1 is only accelerating the 3 kilogram mass. Tension 2 is accelerating the 2 and the 3. I think later on when I solve for the tensions, I better find that tension 2 is bigger than tension 1. If not, I've messed up. What are the forces acting on the 5 kilogram mass? Get the obvious one. What else? What else? Which way? What? What do you call it? Okay. What else? So I'll put an arrow there, and I go just so it stands out. The 20 newtons is pulling everything, but it's not attached to that 3. It's not going to appear in the 3 kilogram mass equation. It's not going to appear in the 2 kilogram mass equation. It'll only appear in the everything or the 5. Who's winning? So what you're really saying is, as I walk along the rope, anything that ends up pointing to the right is going to be winner plus. Anything that ends up pointing to the left is going to be loser minus. That's really what I mean with my winner minus loser shtick. So F applied. Keep going. Minus tension 2. Keep going. Plus tension 2. Keep going. Keep going. Keep going. Yes. You know what? I'm going to go M all times A. You could put M1 plus M2 plus M3 in brackets if you want, but this is where I kind of get lazy and I say, all of them. Pierce, you navigated that so well. You deserve a reward. Stretch, come on. Oh, twice the tension, Pierce. Oh, I like this. It's like a double spa treatment. Oh, good stuff. Minus tension 1 plus tension 1, minus tension 2 plus tension 2. In fact, Pierce, how will I get the A by itself? So you're telling me A equals the applied force divided by the mass of all of them? What was the applied force? What's the mass of all of them added together? Check again. What? What? You're right, loud and proud. 10. In your head, Pierce, without a calculator, what's my... Oh, wrong button here, Mr. Duke. What's my acceleration? And I'll go to 2 sig figs, so I'll go 2.0, and it's meters per second squared. Isn't that neat? Now we want to find tension 1. Which mass looks cleaner to find tension 1? What mass would you choose to use if you were thinking clearly? Yeah, I know there's also a tension 1 on mass 2, but that's got way more gunk on it, so... I'm not going to redraw the free body diagram this time because you all have it in front of you at the top of the page there. What are the forces acting on mass 1? Sorry? Go ahead. Sorry, I'm going to change my question. Said the wrong question. Alec, my friend, looking at mass 1, what's the equation? Who's winning? Which one? There's 2 of them. Thank you. Who's losing? Oh, so it's going to be tension 1 equals? Which M? There's a bunch of... Huh? Okay, let's be careful now. I'm going to stop reminding you and just glare. Hey, what was mass 1?
3.
What was the acceleration?
2.
Please tell me you can do that one in your head.
6.
And I'll go 6.0. And it's a tension. What are the units for tension? Yep. What if I wanted to find the tension in the second rope? Which mass would be cleaner to use? It's about a 50-50 split, but I noticed the notes are suggesting that I use chord 2. You've all just changed the page, yes? So I'm going to stay here on my free body diagram so you have it in front of you. So find the tension from chord 2. Josh, what would I write? Looking at my free body diagram, to find the tension 2 from mass 2. How could I write? Give me an equation just for this guy. Who's winning? Write that down, everybody. Any other winners, pluses? Nope. Who's losing? What is that going to equal? Which M? Thank you. So you said this. And we're trying to find tension 2, so we'll just plus that over. So tension 2 is going to be M1A plus M2A plus tension 1. Josh, what was M2?
2.
What was A?
2.
Plus. What was tension 1, Alec? What was tension 1? Get it in your head. There you go. How big is tension 2? You know what, Josh? I'll bet even you can do this one in your head, too. I think so. What do you get? I'll go 10.0 just so I go to 2 or 3 sig figs because 10 is technically 1. Units, newtons. Then I wrote here, consistency check. You know what? I'm feeling kind of lazy. I'm just going to do this without writing anything down. The equation would be 20 minus, sorry, here for you guys. No. Here. 20 minus tension 2 equals M3A. I'd have a minus in front of the tension 2. I'd do the swappy dance. I think I'd get 20 minus M3A. Does that also give me 10 newtons that Josh just gave us? That should be cool if it did. There's my check. What if there's friction? Oh, sorry, before I do friction. What if we're hanging over a cliff? If we have a hanging mass and no external force, we need to understand that it's the weight, that's the mg of the hanging mass that accelerates the system. So example 3 says, identify the net force on the system and then find the acceleration of the cord tensions. Okay. Connor K, let's do this one. Is there friction in example 3? How do you know? Okay, mu 0. What are the forces? I start on the left and work more. You don't have to, but I want to be organized. What are the forces acting on that 2 kilogram mass? Get the obvious one. I got to be fussy. M1G? Yes, because there's more than one mass. What else? Normal force number 1, I agree. What else? What else? Oh, good. So nothing. We're done here. Good. So mass 2, what are the forces acting on it? Get the obvious one. What else? By the way, I'm glad you made that mistake. You said Fn. Are we on a surface? Can there be a normal force if we're not sitting on a surface? No normal tension. There's my free body diagram. What's the net force that's causing this to accelerate? M2G. Now you need to imagine that we're sitting on ice. If you're sitting on ice, the 4 kilogram mass is going to pull the 2 kilogram mass over the cliff. And even if it was the other way around, sitting on ice, if that was a 4 kilogram mass, this 2 kilogram mass will pull the 4 kilogram mass over the cliff because this 4 kilogram mass has no way to pull back because if it's sitting on ice. Okay? You can't somehow hang something over a cliff, tie a rope to the rock at the top of the cliff, and then suddenly the rock starts crawling backwards on its own, lifting things up. Life doesn't work that way. So you're either going to accelerate down the cliff, or if we bring in friction, you might be just stuck. Connor K, then, let's write an equation. Who's winning? Now, our equation is going to run along the rope. A rope can cause forces to change direction. So last unit, I always said to you, never put a horizontal into a vertical or a vertical into a horizontal. Here, I'm going to say, write the forces that end up going along the rope, because we are going to turn 90 degrees, and we are going to be putting forces that appear vertical into a horizontal equation, or that appear horizontal into a vertical equation. You know what? It's rope and not along the rope. So you've just decided with your winner that anything that ends up pointing down when it gets to that side is going to be a winner plus. Anything that ends up pointing up when it gets to that area is going to be loser minus. What's the equation? Keep going. Walk along the rope. Walk along the rope. Is that it? Is that it? Is that it, folks? Pierce. Yeah. Wait, what about M1G? No. Is that along the rope? Don't start sticking forces in that shouldn't be there. That's it. What's that going to equal? We have forces from more than one mass on the left. We better have more than one mass on the right. Ah, Connor, you've earned it. Good stretch. What happens, Connor? Connor K, what happens? Why'd we stretch? Give me the punchline. Thank you. Let's find A. How to get the A by itself, Connor? Divide what? So it's going to be M2G divided by M1 plus M2. What was M2, Connor? 4? Times 9.8 divided by 2 plus 4. I doubt this will work out evenly. What do you get, folks? Is this a fraction? Is there more than one thing on the top? Is there more than one thing on the bottom? You're going to get, well, it's roughly 20 divided by 3. It's going to be 6.53333. Okay. I'll write 6.53, but I'll keep that number stored on my calculator, and of course it's meters per second squared. Is that okay, Seth? What else did they want me to find, Connor? It said find the acceleration and tension. Which mass is going to be cleaner to use to find tension? M1. Why? Let's write an equation. You're right. Let's write an equation. I'll call this part A, find acceleration. Part B, write an equation for mass 1, Connor, that would find tension. Who's winning? Who's losing? M1G, that's along the rope, is it? How dare you? We're just writing forces on mass 1, and you're way overcomplicating this. Who's winning? Tension. Who's losing? What force is pointing to the left in that free body diagram right there? Help them out, folks. It's so easy that it's tough. Nothing! Nothing! Who's winning? No, who's winning? Who's losing? No one. So what's my equation going to be? Tension equals. Don't start putting extra forces in there. Oh, which mass are we looking at, Connor? Which mass are we looking at? M1A. Oh, we got the T by itself already. It's going to be, what was M1? 2 times 6.5333333. 13 point, what, 13.1? Double check me. Someone needs to type this on their calculator. 13.1? Newtons. Okay. Don't start thinking, well, gravity's on my diagram, must use it. You know when gravity is going to show up? M1G will show up if there's friction. And the reason M1G will show up if there's friction is because friction is what times what? Mu times the? I don't know the normal. Otherwise, it's not going to show up. Now, you're saying, well, Mr. Dewick, shouldn't that mass be slowing it down? It did. The mass slowed it down by appearing in the bottom of this fraction. Since you're dividing by a bigger number, you get a smaller acceleration. Built-in error checks, by the way. Things you can make sure you haven't typed it wrong on your calculator. Supposing we cut the rope. Supposing there was no rope. Mackenzie, what's the fastest this could be accelerating if we cut the rope? What's the acceleration in free fall? You know this. 9.8. The negative isn't popping up this unit. 9.8. So I can already tell you the answer for A has to be less than 9.8. If you're typing on your calculator and you're trying to find the acceleration and you get an answer of like 17, you've made a typo. Or you've got a wrong winner or something. Okay? It says, for problems that involve friction, we can still use the system approach to find the acceleration, but the tension calculations are tricky. Explain how you would find the acceleration of each system. You know what? Let's just do one. Example 5. I feeling good? We're going to do it anyways. Kiana, is there friction in this question? How do you know? Hey, what's mu? I don't know. What's mu with... Okay. We're going to find the overall acceleration by writing an equation for everything. And then to find specific tensions, we'll go look at specific masses. So what are the forces acting on this 5 kilogram mass? Get the obvious one, Kiana. What else? I'll call it normal force number 1 to go with mass number 1. What else? Which way? You know what? I'm going to call it friction force number 1 to go with mass number 1. What else? Tension. To the? Right. Those are the forces acting on mass 1. What are the forces acting on second mass? Get the obvious one. What else? Normal force number 2. What else? Tension pointing left. What else? What else? What else? And I'll call that friction force number 2. Now, there is going to be a question in your homework where there's a coefficient of friction for the first mass and a different one for the second mass, because second mass is made out of different material. So it should have a different coefficient of friction in real life. Okay? Or you may see a question where one is on a rough surface and the other one's on ice. Or you'll see a question where one is on wheels. That's my way of saying you could ignore friction for that second one. Okay. Have we got our diagram? We labeled everything? Who's winning? If anything. Now, if the applied force isn't winning, if friction is so big that this thing isn't moving, how will I find that out? I'll get a negative acceleration when I try and solve for A, and that's when I go back and say, I got the wrong winner. Okay. So what's my equation going to be for part A, Kiana? We're going to write all of the forces along the rope. Again, this is important, Alec. This is important, Connor. All the forces along the rope, so we're not sticking extra forces in. Who's winning? You said applied force. So anything pointing to the right is going to be winner plus. Anything pointing to the left is going to be loser minus. So talk me through it. Yep. Oh, good stretch. I love doing... Mr. Dewick. What, Josh? Do we really have to write tension if we know it's going to cancel out? I won't take marks off if you don't. I have to be honest. I still get a little giggle every time I get to cancel out tensions, so I tend to do it that way. Trying to find the acceleration. How would I do that, Kiana? So if I hear you, you're telling me it's going to be the applied force divided by M1 plus M2. The applied force was 20. 5 plus 3. Oh, wait a minute, Mr. Dewick. I'm doing last question. Sorry. Minus... So it's going to be divided by M1 plus M2. You said that, yes? Minus, stop, friction force number 2. Friction is what times what? So it's going to be mu normal force 2, and then minus mu normal force 1. How big is the applied force, Kiana? Minus... What's mu? I don't know. What's mu with you? What's mu? I don't know the normal force. Oh, but look. Okay, got to be careful. M2, this is why we label. What is M2? 3. We'll do that in one step. We'll feel brave. Minus, hey, what's mu? 0.15. Normal force number 1. I don't know normal force number 1. Oh, but look. Now, today still you'll notice normal force number 1, Daniel, has been equal to mg. That's going to stop eventually, so make sure you never just think, oh, mu mg. Look at your diagram and figure it out. So it's going to be 5 times 9.8. Find what you're looking for, kiddo? Okay. All divided by... I'm going to be bold and go 5 plus 3 in my head. What do you get? 20 minus 0.15 times 3 times 9.8 minus 0.15 times 5 times 9.8, close bracket, divided by 8. Did I miss any typing? I think I'm good. Get 1.03? We're not done. It said A, find the tension, but what did it want us to find for part B? Sorry, it said A, find the acceleration. What did it want us to find for part B? What would be the cleaner mass to use for part B to find tension? I think M1 slightly. So I'm going to use M1. So now we're looking at M1. Who's winning? Who's losing? Equals. To get the T by itself, plus it over, I'll get tension equals M1A plus friction force 1. What was M1? Was it 3 or 5? 5? A 1.03 plus, you know what? I think I have friction force number 1 written right there, don't I? 0.15 times 5 times 9.8. Here it's a plus sign instead of a minus sign, but it's going to be the same magnitude, same numbers. 0.15 times 5 times 9.8. 5 times answer button plus 0.15 times 5 times 9.8. And I get a tension of 12. Oh, nice. 12.5 even. What about if we're hanging over a cliff? Like that. Okay. I think this is the last one. Cool. Let's plan our attack. It says find the acceleration, find the tension. How many masses are there, Connor L, in this question?
3.
How many ropes are there then?
2.
How many tensions will there be?
2.
Okay, I got that. Let's start labeling. Oh, is there friction?
Yeah.
Alrighty. What are the forces acting on this 4? Get the obvious one.
M1G.
I agree. And normal force number 1 up.
Yeah.
What else?
Tension.
Is there more than one rope?
Yeah, sorry.
Tension 1. What else?
Friction 1.
Pointing?
Left.
Yep. What are the forces acting on the 3 kilogram mass? Taylor, get the obvious one.
M2G.
I agree. What else?
FN2. And tension 1.
Which way?
To the left. And
Yep.
Force of friction 2 to the left. And then tension 2 on the right side.
Nice. Risa, what are the forces acting on the 5 kilogram mass? Get the obvious one. Connor K, is there a normal force? On mass 3? Is there a normal force? No, it's hanging in midair. Now again, there's only 2 possibilities. Either everything is sliding down and to the right, or these friction forces could be so big that this is at rest. But there's no way that inanimate masses suddenly start crawling backwards on their own and lifting everything up. So, with that said, if anyone's winning, who's winning? Reese? So anything that ends up pointing down when it gets to this side is going to be a winner plus. Anything that ends up pointing up when it gets to that side is going to be a loser minus. And I'll have to use my imagination to follow the forces around that little pulley bend, but I can do that. I watched Sesame Street growing up. What's my equation then, Brisa? equals? Good. Although I might have said it with a bit more joy in my voice. M3G minus tension 2 plus tension 2. I'm just saying. But I saved this double helping of stress relief for you, Brisa, my joy. Oh, twice the tension canceling out. I like that. So I guess to get the A by itself, I'm just going to have the dividing by 4 plus 3 plus 5, the mass of all of them. M3G minus friction force number 2. Friction is what times what? Mu times the normal force. I don't know the normal force. Oh, but look. I think it's going to be mu M2G. And then minus mu M1G. Yeah? I can shorten this fraction bar a little bit. So it's going to be 5 times 9.8. By the way, can you see how you could check ahead of time if it is going to accelerate? Calculate both frictions and compare them to M3G. If both frictions, when you add them up, are bigger than M3G, this ain't going anywhere. If they're smaller, it's going to accelerate. Or you could just not care, try solving it, and find out if you get a negative acceleration. And honestly, Kiana, you smiled. I do that half the time because sometimes it's less work to solve the silly thing than it is to try and pre-solve it to find out whether or not it's solvable. Minus 0.2 times 3 times 9.8 minus 0.2 times 4 times 9.8, all divided by 12. I added 4 plus 3 plus 5 in my head because I can. What'd you get? I'm trying to remember. I think this actually does not work out to a repeating decimal. I think you get a half decent answer, like 2.6 or 1.2, 2.94, and it stops. Okay? Yeah? So A equals 2.94 meters per second squared. Now it wants me to find both tensions. I'll do a little line down the middle. I'll find tension 1 on the left and tension 2 on the right just to be organized. What would be the cleaner mass to use for tension 1? It doesn't matter. You don't have to, but if I was clever, what mass would I use to find tension 1? M1, M2, or M3?
No,
M1. Give me an equation for M1 then, please.
T1 minus M1G.
Just read me. No, first of all, no, it can't be M1G because the rope is this way and gravity is this way. How dare you? Right from the free body diagram.
The mu MG.
Just right from the free body diagram.
Oh, force and friction.
That's all I'm looking for. Friction 1 equals M1A. I'll do the other stuff later, but there's my start. In fact, I'm even going to go haha and plus that over right away. Now I'll start substituting even more. It's going to be M1A plus friction force number 1, which I did write up here. Friction force number 1 was mu M1G. It's going to be 0.24, 9.8. I'll go mu M1G. We'll do one algebraic version just for giggles. So it's going to be, what was mass 1? 4? Times 2.94 plus was it 0.2? Times 4 times 9.8. Do that one in your head, Mr. Duke. Oh, maybe. 2 times 0.2 times 9.8 is point. Ugh. Oh, okay, 0.49. So instead of 2.94, it's going to be 3.44, 3.4. Yeesh. 12, 13. No. What do you get? Do you get something in the 13s? Or am I way off? Sorry? I can't hear you. 17.8. I was way. Is it 17.8? 19.6? That sounds familiar from last class. 19.6, I think. So if you're not getting that, double check. Typos and things. Newtons. What would be the way cleaner mass to use to find tension 3? Sorry, tension 2 as a tension 3. What would be the way cleaner mass to use to find tension 2? Look at your free body diagram. Which one? Sorry? I agree. So what's the equation, Josh, for mass 3? Yeah. Do the swappy dance. It'll be M3G minus M3A. That's a 3. What was mass 3? I've scrolled down. Was it 5? 5 times 9.8 minus 5 times 2.94. I think it should be bigger because tension 2 is pulling both the masses down the cliff, where tension 1 is only accelerating mass 1. So I think it'll be bigger than tension 1, I hope. Well, it's going to be roughly 35, a little less than 35, a little more than 35. Less than 35? What do you get? 34.3? Is he right this time? Because I don't trust. Okay, good. Okay. What's your homework? So I'm doing something a bit different this time. You're going to see some circled and some have check marks. So it goes like this. You ready? Do number 1. If you got number 1 right, you can skip 2 and 3. 2 and 3 are clones of number 1. If you have trouble with number 1, try number 2. If you still have trouble, try number 3. So those check marks are, if you got it right, you can check them off and don't do them. Cross out 4. 5 is good. 5 is hanging over a cliff, no friction. You know what? 6 is hanging over a cliff, no friction. If you get number 5 right, you can skip 6. If you want more practice, do 6. Number 7, 2 masses with friction. I'll assign that. Number 8, 2 masses, 1 hanging over a cliff with friction. I'll assign that. You know what? Actually, I'm going to cross out 8. I just noticed it only wants the equations. I'm going to assign 9, but cross out A, do B. You'll have to do A to do B, but my equations might look a little bit different from their equations. Is that okay? Ten is 2 masses with friction. I think we already did 2 masses with friction. So you can put a check mark next to number 10. If you got number 7 right, skip it. If you need more practice to do number 7, do number 10. 3 masses with friction, 11, sure. 3 masses with different friction, except really you can cross out A and just do B. Find the acceleration and the tension. You'll do A to do that anyways. 13 is nasty. Skip 14. 15, I'm going to put a star next to as being nasty. 15, we're backwardsing the question. We're reverse engineering the question. Up until now, Pierce, I've given you all the masses and I've said, hey, find the tension, find the acceleration. Here, I'm saying, what if I give you the acceleration? Can you find the tension and use that to find the missing mass? I'll be doing that next lesson. But there you go.